Hi everyone, this is a tutorial video on properties of exponents. So I'm just going to walk you through a couple of our exponent rules and give you a few examples as well. Okay, so the very first one we're going to talk about is the product of powers. So when we multiply what we call like bases, so if these numbers here are the same, if we multiply like bases, we add the exponents. So in this case here you could see when we're multiplying a to the m times a to the n, we would be adding the exponents to get a to the m plus n. Alright, so with letters that's a little confusing, so we'll go with some other examples here. So again, not to skip too far down the road here, but y by itself is the same as y to the first. So this, multiplying all with like bases, I'm adding the exponents to get one exponent for the entire expression, which would be 4 plus 3 plus 1, or 8. We'll do the same thing again. Now, don't let these numbers change how you're doing things because they don't have exponents. So negative 3 times 5 is still negative 15. That doesn't change. But I then focus on the variables that are the same, and I look at their exponents, and I do apply this product of powers rule. So x squared times x to the first is x to the third, and y to the seventh times y to the sixth is y to the 13th. Okay? So a quick explanation on why that is. If I have x squared, that is x times x. And if I have x to the first, that's just x. So x squared times x to the first is x times x times x. Well, x times x times x is x to the third power. So we were able to figure out, oh, instead of having to write all these things out, what's ended up happening is the number here is matching the number here once I add them together. So I'm able to use that rule without having to write everything out. So there's your justification for our product of powers rule. Our next rule is the quotient of powers. So when I divide like bases, I'm going to subtract the exponents. So real quick, 6 to the 13 divided by 6 squared would be 6 to the 13 minus 2, which is 6 to the 11th. Okay? And a real quick reminder here, we want to kind of separate this numbers with the numbers, A's with the A's, and B's with the B's. 10 divided by 15 still reduces. So 10 over 15 reduces to 2 over 3 since they both have a common factor of 5. But then I can subtract my exponents here. So in your head you're thinking this, and with my B's I'm subtracting. Again, in my head I'm thinking that. So now I simplify and all my results go into the numerator or the top of the fraction. So I still got my 2/3, a squared b to the 0. Well, b to the 0 or anything to the 0 power is essentially saying multiply by itself no times. Well, b being multiplied by itself no times means there's no b's there. So we could say that b to the 0 is 1 because that 1 represents the placeholder because I'm not multiplying by b at all. So I can just go ahead and continue to simplify. A squared times 1, or simply 2a squared over 3. The justification for this rule here, I'll use my x's to help with that. So let's say that I have, sorry, not my x's, my 6's. So let's say I have 6 to the 5th divided by 6 to the 3rd. So that would be 6 times 6 times 6 times 6 times 6. 5 sixes, and then divided by 6 times 6 times 6, 3 sixes. Well, I could cancel off these because they're all the exact same, and that leaves me with these two. Well, that's the exact same thing as subtracting off what was on the bottom. So 6 to the 2nd is my answer, and that's the same thing as 6 to the 5 minus 3. And that's why we can have that rule of the quotient of powers. Okay. So I already gave you a quick preview about this 0 exponents, and it just, again, just to reemphasize, a to the 0 power was basically saying that we multiply a by itself 0 times. So anytime I get something to the 0 power, I can replace it with this 1 because 1 represents a placeholder for no a's. All right, so this is a to the 8 to the 2 minus 2, or 8 to the 0, which is 1. 8 times x to the 0, that's the same as 8 times 1 plus 5. So that's 8 plus 5, since 8 times 1 is 8, equals 13. Okay, now we're on the negative exponent rule. And the important thing here is if I can convince you not to think about this as a negative number, but to think about this as telling you to do the opposite. You know, historically, something like a squared is a times a, where you multiply a by itself. But if I tell you to do the opposite, well, what's the opposite of multiplying by a by itself? Then it's dividing by a. So the way that we write this is that because I'm doing the opposite here, I'm actually going to end up dividing. So in this case here, 2 to the negative 3 power means do the opposite. So divide by 2 to the 3rd. All right. I could subtract my exponents here because I'm dividing 2 minus 5, which gives me b to the negative 3 power. But then this negative doesn't mean a negative number. It means do the opposite. So divide by b to the 3rd. That negative tells me to do the opposite of whatever I'm doing. So whatever this exponent is telling me to do, if it's negative, do the opposite of that. So if I'm dividing by it, I would multiply by it. If I'm multiplying by it, I would divide. Okay, so now I'm on to the power of a power rule. So when I raise powers to powers, I multiply. So for instance, right here, x squared to the 8th power is x to the 2 times 8 power, or x to the 16th power. When I raise powers to powers, I multiply. Y to the negative 3rds to the negative 4th power is y to the negative 3 times negative 4 power, or y to the negative 12 power. Now remember, don't think about this as a negative. Think about this as do the opposite. So that would be 1 over y to the 12th because I'm dividing by y to the 12th. Again, the way that I want to think about that is, again, when I raise powers to powers, I'm going to end up multiplying. So let's take a look at what x squared to the 8th actually looks like. That'll be x squared times 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 x squared. 1, 2, 3, 4, 5, 6 times x squared times x squared. 8 times. So then we know that we can add the exponents. 2, 4, 6, 8, 10, 12, 14, 16. And that's what we had. So that's why we're able to say when I raise powers to powers, I multiply. Now I'm going to simplify this here, and I'm going to justify it by explaining which law I used each time. So here we go. First thing I want to do is recognize that this is given information. And the very first thing to do is to kind of simplify my numerator. So I'm going to multiply the coefficients together. 2 times 4 is 8. 8 times 3 is 24. So I just multiplied those together. Now I'm going to concentrate on my x's. X squared times x squared times x to the 1st. Remember, when I multiply like bases, I add the exponents. So 2 plus 2 is 4. Plus 1 more is 5. So this will be x to the 5th power. All right, now I'm on my y's. Y to the 4th times y to the 4th. Add the exponents. 4 plus 4 is 8. Y to the 8th. And then now I've got my bottom. 3 x to the negative 3 power and y to the 2nd. So all I did here was simplify by multiplying. So I simplify by multiplying. Now, if I wanted to get really specific about what I did, is when I multiplied, I said a to the m times a to the n equals a to the m plus n. So if you're going to write a law, you can write it like this instead of having to spell it all out. So I wrote simplified by multiplying, but this is what we were able to do with our exponents when we multiplied like bases. Okay, this is how I'm going to write the rest of the laws, just so you know. All right, now I'm simplifying. I'm going to go ahead and take my 24 and my 3. Those are normal coefficients, so I could reduce those. 24 divided by 3 is 8. So I know that I've got an 8. But now when I divide, I subtract exponents. So this would be x to the 5 minus a negative 3, and this would be y to the 8 minus 2. And again, that's going to help me out simplifying wise, because I'm going to end up with no more fractions. All right, so what that would then look like, I used the a to the m divided by a to the n means a to the m minus n. When I divide like bases, I subtract the exponents. So now I'll simplify, and I've got a 8 to the 5 minus negative 3 is the same as 5 plus 3, or x to the 8th power. 8 minus 2 is 6. Okay, so now I'm checking to see, do I have anything else, any negative exponents, anything to add, subtract, multiply, or divide, anything that needs to be combined. And I'm looking here and I do not. So now I'm finished. So this would be what my final simplified answer is. And I would just kind of box it in here. So the two laws that I was able to use were this multiplication and this division law. And then the exponents, when you multiply, you add. When you divide, you subtract. Okay, our last law that we're going to talk about today is the fraction exponents law. And the connection that I need you to make is that the numerator of the fraction exponent is the same as the root on any radical we take. So what that's basically telling you is that the number here, the root, is the number of that I'm dividing the exponent by, or the number of groups of factors that I make in an effort to try to simplify the radical. So let's show you what I mean right away. So x to the 1/2 power, my denominator is 2. So that means when I make a radical, this number here would be 2. Now, a lot of times you'll see it blank, and it's an understood 2, but if you put a 2 there, it's okay. It doesn't hurt the process. And then the numerator stays with the base here, and it goes underneath the radical. Let's try that one more time. And then we've got another square root and 9 to the 1st power. Well, in number 1, I don't know what x is, so I can't take the square root of x. But I know what 9 is, so the square root of 9 is actually a nice number. It's 3. That won't always work out nicely like that, but in this case it did. All right, how about number 3? The 3 is my denominator, so that means I'm dealing with a cube root, and then x to the 2nd. Now, I go to do maybe a factor tree to see if I can pull out any of my x's. Unfortunately, I only have 2 x's, and that's not enough to make a group of 3, so unfortunately, I have to leave it like that. I can make it more complicated. I can raise things to the 1/3 power, and that's going to then require me to simplify multiple places. So let me show you my thought process on something like number 4. So right away, I can make a cube root to go with this exponent, and everything in these parentheses would now be underneath the radical. But the way that I think about this in terms of simplification would be to leave the number, the cube root of 3, underneath the radical, but then I keep thinking about the exponents in terms of fractions. So remember, this root is the denominator on the exponents. This root is the denominator on the exponents. So now that's how I'm thinking about it. So then I can ask myself, okay, does the cube root of 3, does that simplify? Are there any factors of the cube root of 3 that are perfect cubes that I could take out? The answer is no. So it's going to stay like it is. But 3/3 is a fraction that will reduce. So 3/3 reduces to 1. So I can rewrite this as x to the 1st power. 6/3 is a fraction that reduces. 6/3 reduces to 2. So that's y to the 2nd power. And then I just had that cube root of 3 because it didn't change, and so I left it. And there's my simplified number 4. All right, we can make that even more complicated.